given below is a table of values for a function h of x and its derivative h prime of x. So we see h of x and h prime of x here. The functions h of x, h prime, h double prime, and even the derivative of h double prime, so h triple prime, all of these are defined and continuous on negative infinity to infinity. So here we have a table, and we are making a critical assumption that between consecutive values of x given in the table, h of x is either always increasing or always decreasing. Now, of course, reading the question carefully is super important for really any type of question, but especially for the problems where you're given a table, the additional information that they give us, these usually tend to be really important. So you need to pay attention to this, because when I just give you a table, we know what's happening at -2, we know what's happening at 0, but in between -2 and 0, unless I give you some additional assumption, you have no clue. Anything can really happen between -2 and 0 here. For example, let's say I ask you, is h of x concave down at x equals to -1? Well, here's a very incorrect way of doing this. You might say, oh, at -2, h prime is -1, so that's negative. And at 0, you have 0. So at -1, h prime at -1 is probably negative, so h of x is probably concave down. But that's not a correct answer. And the correct answer to this question is that there's no information. There's not enough information here. And that's for the simple reason that, of course, the graph can behave in a very wild way between -2 and 0. You can certainly go from concave up to concave down, then back to concave up between -2 and 0. You might argue, oh, I mean, we know h of x is either always increasing or always decreasing in between table entries. Can that help us pin down concavity? And no, definitely not. Because a function can be increasing and concave up, and it can also be increasing and concave down. Like, for example, this would be increasing and concave up. It's making a smiley face, so it's opening up. And this thing is also making a smiley face, so this is also concave up, but now it's decreasing. So whether you're increasing or decreasing, concave up, concave down, those are very independent. So you have no clue whether h of x is concave down at x equals to -1 or not just from the table. But let's say I give you the additional information. So let's say I give you an additional information that the sign of h prime of x does not change in between table entries. So if I give you this additional assumption, then you know h prime of x, since it was negative here and it's 0 here, then the sign should stay negative in between -2 and 0. So now the answer to this question is yes. So these are the ways that additional information can be supplied on top of a table to make these kind of questions answerable. So I'm digressing a little here, but I just want to make the point that you should really pay attention to what's given in between the table entries based on the assumption. Anyway, now let's actually get to the problems. So in part A through C, we want to find the exact numerical value or write any I if there's not enough information. Okay, so let's go to part A. Find the average rate of change of h of x from x equals to -6 to x equals to -2. So you should remember that the average rate of change, this is a concept that you probably encountered pretty early on. And how you find this quantity is by looking at h of -2 minus h of -6, which is how much h changes from -6 to -2. And then you divide by -2 minus -6. Make sure you understand how exactly I'm getting this expression. So -6, if I'm going from -6 to -2, the input is changing by +4. So how do you see that -6 to -2, you have to do +4? Well, I mean, one way is to do -2 minus -6. So this denominator is giving you the change in input. And analogously, the numerator here, since we're looking at h at the final x, final input, minus h at the initial input, -6, this is giving you how much h changed, how much the output changed from -6 to -2. So this is change in output. So when I just look at how much the output changed from -6 to -2, and I divide by the change in the input, which is 4, that's gonna give us the average rate of change. And what is this? H and -2 is -2, h and -6 is 2, so we just get -2 minus 2 divided by 4, so this exactly gets us -1 here. I guess one variation that might be worth remembering is that if the input is time, so maybe this is t, so rather than h, I'll write t for time, and h of t is the position function, then this average rate of change this thing is exactly the average velocity, because velocity is the rate of change, and here you're finding the average rate of change of position. And if rather than a position function, let's say we had a velocity function here, then the rate of change of velocity is acceleration. So this quantity that we computed would be the average acceleration. Of course, you'd have to use correct unit in that case as well, but I guess that's a simple variation that you should be aware of. And another possible variation is rather than giving you these values of h, maybe the question is exactly the same, but maybe now you're given some information about h prime of x. So maybe you're given a graph of h prime of x, or maybe you're given a formula, and you have to find the average rate of change of h of x from this. So that's another possible variation, I suppose. So for example, maybe here h is the position, and you're asked to find the average velocity, and you're given a graph or formula of the velocity function. So how would you do it there? Well, the thing to realize is that the average rate of change of h of x and the average value of h prime of x, these are exactly the same concept, even though the computation might be a bit different. And this hopefully makes sense because the rate of change is the derivative. So the average rate of change of h of x, you probably hope is same as the average value of h prime of x. And how do you find average value of a function? So let me quickly say that because it's going to help us for the next question as well. So if f of x is a function, and we're looking at some interval from a to b, then the average value of f of x on a to b, this is given by taking 1 over b minus a of the integral from a to b of f of x dx. In case you don't really have any intuition on why this kind of expression is the average value of f of x, let me quickly say a couple of words. So one way of thinking about this equality, and I think this is honestly one of the best ways, is to imagine something like this. So let's say you're looking at the interval from a to b, and your f of x looks something like this. So maybe this is f of x. And the question is, what's the average value, what's the average output of this function? And one way of making sense of this is by looking at this particular area under f of x. So I just look at this particular area and imagine that this is made out of Play-Doh, or it's made out of sand. Then you can easily change the shape of. So for example, you might imagine like pushing this part out a little, like compressing this part inside a little, and in doing so, we can change this shape to a rectangle. So we can still go from A to B, but we just played around with this area here. We just shuffled it around. So area is the same, but now we're flat at the top. So we're just reshaping this area to a rectangle. And now it should be reasonable that as long as the area stay the same, that this height better be the average value of f of x. And if you look at this formula, that's exactly what this formula is enforcing. Because if you look at this length is exactly b minus a. So that's the width of a rectangle, and the height of it is the average value of f of x. So this is the width of the rectangle, this is the height, and when I try moving b minus a over to the other side, then we're multiplying height and width of the rectangle on the left hand side, and this side, on the right hand side, we have the area under f of x right here. So this is just a natural way of thinking about the average value of f of x. Another way to think about this formula, if you'd like, is to use the fundamental theorem of calculus. So if capital F of x is the antiderivative of little f of x, so this is exactly saying when I differentiate capital F prime, then I get f of x. So it's like differentiation but going backwards. Rather than giving you f of x and you have to differentiate it, now capital F of x is what I differentiate to get f of x. So if capital F is antiderivative of f of x, then you should know that by fundamental theorem of calculus that this expression, this integral part, is exactly f of b minus f of a. And what is this kind of formula? Well, you should remember we just computed something like this in part A. This is exactly the average rate of change of the antiderivative, capital F of x, from a to b. So all this formula is giving us is the average rate of change in the antiderivative from a to b, and the rate of change of the antiderivative is of course f of x, because when I differentiate capital F, I get f of x. So this formula is giving us the average value of f of x. So again, so that's just a quick intuition for those of you that's not too familiar with this. But I guess the point I'm trying to make here, going back to this, is that if I'm given h prime of x rather than h of x, and you want to find the average value of h prime or average rate of change of h of x, then what you can do is you can just look at 1 over 4 in this case, because that's b minus a here, plus 4, times integral from negative 6 to negative 2 of h prime of x dx. So if like the information you're given in part A, rather than the information on h of x, our information was on h prime of x, you would get the answer using this formula. Now, staying on the notion of average value of a function just a little longer, let me actually give you one more intuition, and it's that the average value of a function does not have to be the same as just averaging f of a and f of b. So average value of a function is not necessarily f of a plus f of b over 2. And that's because average value is really a weighted average in disguise. And it's the weighted average in the following sense. So here, if I look at f of a, that's this y value. If I look at f of b, it's the y value of this point. So when I just average f of a and f of b, so if I do f of a plus f of b over 2, I get a y value corresponding to height of, say, this point. That's the average of the height of this and the height of this. You get around here. But that's not the average value of the function, because the function is almost always pretty close to f of a. And since you're very close to f of a for most of the time between a and b, you're going to give higher weight to the values near f of a than the values near f of b. So what the answer that you get, for example, in this particular function, is that the average value of f of x is going to turn out to be smaller. It's going to turn out to be smaller than this thing. I guess it deserves to be said, when do we have the equality? Well, when we have a linear function, we have the equality. So if f of x looked like this, so if f of x was just a line going through these 2 points, then when I find the average value of this function between a and b, then you'll get literally this halfway point. So for a line, you get the halfway point. Otherwise this weighted average is going to possibly prevent it from having the equality here. So in the original function here, our function is actually below the line here, so our average value is going to be smaller than this. So looking at part B, we are given that the average value of h triple prime of x on this interval is 2. And we wish to find this sort of integral. And something that you should see is that since we have plus, integral behaves very nicely with plus, so we can split up this integral. So really the difficulty here is, what's the integral from negative 6 to 0 of h triple prime of x? Can we evaluate this in any nice way? I mean, the information from negative 6 to 6 of h triple prime of x dx, how can we get information on this? Well, we know the average value of h triple prime of x, and we know the average value can be defined in terms of integral of the function. Here the function is h triple prime of x. So we have all the connections we need. So let's just write down what we have. So since the average value of h triple prime of x on this interval is 2, so rather than f of x, we have h triple prime of x, and the interval is from negative 6 to 0. So we know on this interval, which has length 6, b minus a here is 6, 0 minus negative 6, and you have interval from negative 6 to 0 of h triple prime of x dx is 2. So we know this thing is 12 by just multiplying by 6 to both sides. And now let's actually look at evaluating this integral. Well, we have 5 times, let me split up the plus. Remember, when I have a plus, the integral splits up in a very nice way to integral from negative 6 to 0 of 1 dx plus integral from negative 6 to 0 of h triple prime of x dx. And here we know this is exactly 12. We know this from here. Whereas this part, you can either compute this using the fundamental theorem of calculus, but even easier way of doing this is that the function y equals to 1 is just a horizontal line. So here you have a y equals to 1, and we're looking at the signed area underneath it from negative 6 to 0. So you're looking at it from negative 6 to 0. So the area here, it's just a rectangle. This is clearly 6 times 1, or 6. So we see that this thing turns out to be 5 times 18 or 90.